Hey, what's up guys? Mrs. Thompson here, and today we're covering solubility. Now, solubility is just a solute's ability to dissolve in a solvent, like salt into water. We need to learn the three factors that affect solubility. That's like things that can change the amount of solute that can dissolve in a solvent. Great. First one, most important one, is temperature. Temperature affects solids and gases differently, so we've got two things to say here. For a solid, you've probably experienced this if you've ever tried to dissolve sugar in cold water. If you try to dissolve sugar in cold water, it takes forever. You stir and it doesn't dissolve. If you did the opposite, you put it in hot water, it tends to dissolve a lot quicker. So solids tend to dissolve better in warmer temperatures. So this says most solids increase in solubility. Their ability to dissolve increases as the temperature increases. Gases have the opposite effect. For a gas, what you're doing when you increase the temperature is you're giving it more kinetic energy. Now, if you give a gas more kinetic energy, since the gas, it can actually leave the solution. And so as you heat up a solution that has gas in it, it decreases in solubility as that temperature increases. Now, you've probably experienced this if you've left a can of soda open on the table and it gets hot out. What you come back to is some flat soda. So here's a demonstration of this. I'm going to skip around a little bit. Okay, so what this teacher is doing is he's got two seltzer bottle, and he's going to heat one, leave one at room temperature, and then put one in a cold water bath. And then he's going to open them to see what happens when those are opened. So let's see. Here is the room temperature one. So the molecules are just moving at the speed of room temperature. He opens it, and some fizzes out. All those gas molecules escape because they have enough energy to escape. Let's see the cold one. So those gas particles are moving slower, and so as he opens it, let's see how many escape. Oh, well, you can see there. Just cleaning the bottle off. All right, here we go. Few bubbles come up, but not a whole lot. Not too exciting. Let's see if we can find the one where he puts it in hot water. There it is. And that one makes a huge mess because the gas particles have enough kinetic energy to leave, so they leave. They actually have lots of energy, so a lot of them leave the solution. So that's a good demonstration to show you that as temperature increases, the solubility of that gas decreases, and it actually leaves the solution. That's why we say it decreases. All right, so then what about the second thing that affects solubility? Well, pressure can affect solubility if we're talking about gases. Okay, so one way to keep that soda in the gas particles in that soda is to keep the lid on, right? If you take the lid off, what happens? The bubbles come out. Why? Because as those bubbles start to come out in a closed container, they kind of bounce around in here and then bounce on the surface of the liquid, and that bouncing creates pressure. If you open it, you hear that sh sound. Why? Because these bubbles that are above the liquid are allowed to escape. And then you have room for more to come out and escape. And so here we go. Pressure for gases only. All gases increase in solubility as pressure increases. Which means keep the lid on, keep it closed, so that the gas particles want to stay in the solution instead of escape. All right, so the third thing is the nature of the solute. Things that are alike can dissolve things that are alike. So like dissolves like is the key word here, or the key term we use. So ionic compounds, because you have a positive end and a negative end, are very soluble in water because water is polar. Water has a positive end and a negative end. So I'd like you to draw that. Just so you remember, water is polar. Hydrogens become positively charged, slightly positively charged, and the oxygens become slightly negatively charged. And they attract things that have charges. Okay, just like we saw in that video before of sodium chloride being pulled away from each other and forming a solution of sodium chloride in water. All right, I'd like you to draw this table. All right, and we're going to go through and see if these things will dissolve. So we've got on the side, we've got solutes. Across the top, we have solvents. And then the difference here is whether they're polar, non-polar. And then I have even thrown in ionic. All right, so let's say we are mixing a polar solute with a polar solvent. Now remember, like dissolves like. So if like dissolves like, these are soluble. They will dissolve. The alcohol will dissolve in water. Great. Let's try the next one. We're going to put a polar solute in a non-polar solvent. The example here is if you put alcohol in fat. Okay, so if we do that, when we put the polar solute in, it's insoluble because they're different. So they will not dissolve. All right, what about non-polar solute in a polar solvent like oil and water? That's insoluble. It will not dissolve. They're two different things. So just remember, like dissolves like. All right, and then non-polar and non-polar like oil and fat. Oh, there's oil and water. Didn't dissolve. Oil and fat are soluble. In fact, here's a picture of someone making soap. Why does soap clean your body? Because it's made out of, well, it used to be made out of rendered fat. And so they take the fat and then you're able to clean your body because you've got lots of oil. So the fat helps to dissolve the oil on your body and you become clean. Next is, what about ionic and polar? Now, an ionic solute is very similar to polar because it has charges, so it's also soluble. But an ionic will not dissolve in a non-polar solvent. So you can't put salt into fat and hope that it'll dissolve. All right, next. How can we change the dissolving rate? How can we speed up how much will dissolve? So draw this table, skip 3 lines for each, and then we'll fill this in. All right, so we're going to go through each one at a time. All right, first, surface area / particle size. All right, for a solid solute, if we want to get this to dissolve faster, here we've got some sugar cubes and some granulated sugar. Maybe you've experienced this. Which one will dissolve faster? The granulated sugar over here on the far right, or the sugar cubes? Hopefully you said it's the granulated sugar. With the smaller particles that are broken up, dissolve faster. So this is decreasing the particle size will increase the surface area, meaning it has more surface to surround, which will increase the rate. Now, increasing the surface area, usually students get thrown off by this. If you make the particles smaller, you are actually increasing the surface area. We'll take this example here. This is a sugar cube. If we cut it into pieces, now we have more surfaces that we didn't have before. So we have this side, this side, this side, this side, and then even under here, and then on the far wall there. So we have more surfaces to attack for the water molecules to come in. And then if we even break it up even smaller, then you have way more surface area, all the in-between spots that you didn't have before. Gases, you can't really crush up a gas, so you can't change the surface area of a gas. How about stirring? Can stirring change how much a solid dissolves? All right, so for stirring, you probably have done this. You've probably made Kool-Aid by stirring in the sugar, and it dissolves faster when you do that. So stirring increases the rate of dissolving by exposing fresh solute to solvent and adding a little bit of energy for those particles to come into contact with each other. For gas, it has the opposite effect, because remember that if you give gases energy, they escape the solution. So for stirring with a gaseous solute, it decreases the rate. You wouldn't want to take and stir your soda because all the gas particles would come out and they'd become flat. About the amount of dissolved solute. So the amount of dissolved solute, that's how much is in it already. So if you add more solute to a solution, what will that do to the rate? It will actually decrease the rate. So if you keep just trying to add more and more salt because it's not dissolving, it's actually going to have the opposite effect than what you think. It's actually going to make it not want to dissolve any faster. It just slows it down. Okay. It'll eventually dissolve until it reaches saturation, but it'll take longer to get to saturation. All right, for a gaseous solute, adding more gas will also decrease the rate. Same thing. All right, temperature, last one. Solid solute versus gaseous solute. So what about solid for temperature? We already discussed that increasing the temperature increases the amount that can dissolve. So it also increases how fast it can dissolve because it's causing more collisions, more interactions between the solute particles and the solvent particles. Okay, for a gas, if you increase the temperature, remember that gas escapes, so it decreases how fast it will dissolve because you're giving it more energy to escape. Okay, and that is it for solubility.